very happy. I'm very happy to welcome Mr. Levin, who was here at IMPAN this last year, and he will give us a talk about his recent breakthrough in the theory of main dimension. Please.
Thank you very much for inviting me to give the talk. This is my last week in also in IMPAN this year, and you make me work hard. Okay. So I will present instruction of a free reaction by isometries on a compartment space, which is not embeddable into the cubical field. This is a joint work with Dranishnikov. Calculation. G is a discrete group, and Y is a topological space. It's a full sheet. YG is a space with a product topology with a sheet X, and just by the sheet of the coordinates. G is an element of G, and the coordinates of GY, Y is a point in YG, is determined by the coordinates of Y, by just shifting the coordinates by G. So it's for if G is not an abelian group, then the multiplication from the right by G. So I will remind you the definition of the mean dimension of Z action or the homomorphism from X squared. This notion is introduced by Dranishnikov, and for Z action, it can be defined with this simplified way. So the Z action of on the compartmented space X. And this action is generated by the action of a generator of the generator. So we say that the mean dimension of the dynamical system is bounded by alpha. Alpha is non-negative real number. If for every beta, once again, real number bigger than alpha, and epsilon bigger than 0, there is a cover, open cover of X such that mesh U under the I iteration of T, and mesh stands for the maximum or the supremum of the diameter of the elements of the cover. Okay, will be less than epsilon for sufficiently many iterations I. Namely, so the number of iterations should satisfy the inequality. It must be bounded by the order of U. Order of U, it's the multiplicity of U, the maximum number of the elements having non-empty intersection. Or you can reduce it by 1 in the style of the English route, and Y, so it doesn't matter. It will be the same result. By the way, you can define topological entropy exactly in the same way. You just replace the order of U by log of the number of elements. And of course, we are talking about finite open covers of things. So immediately from the definition, you can see that any action by isometries of mean dimension 0, because we can go infinitely many times. We can infinitely many times iterate our cover without enlarging the meshes. It's not difficult to show that if you consider the K cubical sheet, then the mean dimension is exactly K. So in terms of the mean dimension, we use the covering dimension. And once again, for the definition, it's quite obvious that if you have a subsheet of of a cubical sheet or invariant dynamical invariant setting in a dynamical system, then the mean dimension of that space itself will be bounded by the dimension of the space. So we get immediately the mean dimension of any space which is equivalently embeddable into a cubical sheet is most K. Okay, so let me just remind some classical results regarding the invisibility of dynamical systems in cubical sheet. So probably this topic started with work of Jaworski in 1974. So he proved in his PhD that if one has a free dynamical system, free Z action on a finite dimensional compartmented space X, then it's embeddable into the sheet on the 0, 1 interval. Okay. So, a priori point. So, no finite only. Okay, yeah. It's clear that this result suggests the problem is the restriction about the finite dimension of X is essential. And it turned out to be not a simple outcome. It had to wait until Gromov introduced that notion of mean dimension, and then in Lindenstrauss and Weiss, constructed the meaning of the action in compartmented space with mean dimension bigger than pi. And by the results that I just mentioned, so it implies that such a dynamical system does not invest into the shift on the 0, 1 interval. And almost simultaneously, not almost, exactly simultaneously with that result, Lindenstrauss has this beautiful theorem that says that every minimal dynamical system on a compartmented space with mean dimension bounded by constant speed, positive constant speed multiplied by k, it needs invariant embedding into the K cubical sheet, provided the mean dimension of so I think I mentioned that. And the constant C determined by Lindenstrauss, maybe it was not optimal one, but anyway, so it can be slightly improved, but it's not the point. Okay, so P explicitly stated 1/60, so 6, and the problem was to find the optimal estimate for C. So in earlier work, Lindenstrauss and the promoter showed that it can be bigger than 1/2, and Gutmann and Tsukamoto, very impressive work using signal processing, showed that this optimal estimate is achieved. So you can construct such an embedding with C equal 1/2. Okay, it's clear that non-trivial minimal dynamical, not finite dynamical systems are free. So it's reasonable answer in the opposite direction to that problem. Counterexample of Levin Strauss and okay, and it's once again it's natural to ask to what extent that the restrictions that the system is minimal is essential for Levin Strauss result. Actually, Strauss proof is slightly more general for his theorem. He looked for extensions of non-trivial minimal system. But what is essential in his proof that he introduced the so-called level function. A key tool for constructing embedding, and it was later generalized by Jonathan in the so-called market property. So it singles out exactly that property that allows to construct level function. Okay. So last result is proof not only for minimal system, but for the system having the market. Okay, before we go to this result, I would like to mention that for many years it was unknown if every free Z action or compact metric space has the market flow. And only recently, at least it was published recently, the result is slightly older, it was shown by a group of Japanese mathematicians that I remember only one name was Tsukamoto. Because of that there are three actions, Z actions, not having the market. So, okay, the market property is not really ready. Maybe I will mention that we will define the market property in connection with another connection with another property, another result. Okay, but Tsukamoto and his co-authors constructed an example reaction without the market property, but that example was infinite dimension. It is a mean dimension, is infinite dimension, and your previous postdoc Rushi, right? Okay. Constructed such dynamical system is arbitrarily small in dimension, but still bigger than zero. Okay. Okay. So it says that the technique used for level function for every technique relying on the level function for marker property couldn't lead to generalization of the Lindenstrauss result to free action. But still, I believe it was believed that such a generalization is possible. In the paper of Tsukamoto with his co-authors, they even conjectured that it's possible for a dynamical system with mean dimension zero. I believe they explicitly state that conjecture. And it turns out that no. So Hinderstrauss result does not admit the generalization to free Z X. Okay, so actually I would like to present or outline the proof of this result. So there is a freeze reaction by isometries on a compartment space which is not embeddable into cubical sheet. Okay. So already mentioned, reaction by isometries have a new dimension zero, and not only in dimension zero, also the logical entity is zero. Okay, so if this result is proved, we even have conjecture to come up. The English how the result extends to the. So the essence of this result lies in algebraic form. Okay, and this immediately follows from the following box of Ulam tie theorem. So here is the wording of the theorem. So P is a prime number. So for every prime number, there is a sequence of natural numbers and such that the product of the spheres, you know the product by X, of the spheres of odd dimensional of things. So I should be substitute, not okay. 2 and I minus 1. So let me correct it. So we create each sphere with a standard free action. So we just embed this sphere is the unit sphere in the product of and I copies of the complex plane. Okay, and we take rotation for each complex. Okay. I believe it's not important for that result, so we can take any reaction, but it's better to work with the standard action because in some point to turn into the simplicial action or the cell action. It's more convenient to work with the standard action. Of the cyclic group. So we give each sphere with a product of cyclic P to the power I group. Okay, and now we consider the diagonal action of Z. Okay, what that means that each GI is a cyclic group, and we can take the action of a generator of Z. Okay, so for each factor of the product, we have a homeomorphism, the action of the generator. Okay, and we define the action of the generator of Z on X. Way the I for the between the of X. By this I mean the diagonal action of P, and this is the action of a generator. Okay.
So when you write the standard free action? Do you mean some specific actions, some rotations, or what?
Yes, by rotations. We embed the sphere into C to the power n, it's a complex plane, and rotate each coordinate, complex coordinate.
So where there is no is the relationship between how GI acts on it and how the integers act on it? And how the capital GI acts on it and how the integers act on it? Is there a relationship between them?
The generator is
Diagonal actions.
T is the action of the generator. Or you, in other words, so you can consider each sphere with its dx. You just take the epimorphism from Z to the sigma. Okay? So all the spaces here are Z spaces, and you take the diagonal action of the Z. Okay, it will be the same. Okay. So the theorem states that somehow we can find a sequence of natural numbers, a mysterious sequence. So actually, we cannot find the sequence in existence here. If such a sequence exists, it's very interesting problem to constructively to give a constructive estimate on n i's. Okay, so the approach of this result is essentially construction. There is no, at least I don't see any way to find estimate on the number. But there is such a mysterious sequence of n i's. Having that wonderful property that actually gives a name of the theorem, it's a Bolshevik type theory. So for every k and every map to x to k-dimensional Euclidean space R, there is a point of x such that the image of the orbit of x under the action of z consists of at most p to the power k minus 1 point. Okay? So if k is equal to 1, so this there is an orbit that goes to a singular. Okay, definitely we cannot resolve this property for higher dimensional Euclidean spaces, but still we keep the finiteness of the image, and we need to increase the lower number of the points in the orbits by the power of P.
Excuse me. So there are no medications for number n. There's
Also cool. If you take the circle and any map from the circle to the real life, then you will have two total points. Okay? And map is continuous. Okay. But it's not continuous. But we have even a stronger property if we consider the map induced by F. Okay, so the map F goes from X to we will go to the V sheet. Okay, and we define the V-map, equivariant map from F is a sheet. This net is equivalent and is defined in the following way. If we take a foil here, we need to determine the foil. The foil in the product. Okay, so it will be F E to the power I. Okay, and T is the action of a generator of C. Of a generator of C. Okay, so it's easy to check that this net is equivalent with respect to the shift action of Z on the product, the left shift. On the product, what else I wanted to say, and actually any map, equivalent map to a full sheet comes from a map induced by a map to the zero coordinate of the sheet. Zero coordinate, I mean the identity coordinate of the sheet. Okay, so it's not not the property specific for the action we have to check it. Or the constructed equivalent maps to the full sheet. Okay, so the additional property says that if we consider the extension of the map induced by denoted by FC, then we will result exactly the same property. Okay, so this is the variant map. The image of the orbit F will have at most p to the power of k minus 1 coordinates in the sheet. In the sheet. Okay. I believe it's quite obvious. The theorem implies the result of. Okay, so exactly this answer is not embeddable into a cubical sheet. For any dimension of the sheet. Actually, it says even more. It's not only that we cannot embed this action into a cubical sheet, there is no orbit resolving map to the cubical sheet. Okay, so we need to, we cannot send injected the orbits of the space to a cubical sheet.
But how special is RK? Can you replace RK?
It's not special. Not special. That's simplified. More basically, in the people, I give a more general formulation of this here. Okay. I believe it's possible to skip the direction that the multiple theorem implies that the result about. Okay. It's simple. There is nothing big. And there is nothing here, not only big, nothing at all. Okay. We will try to outline the group of that zero for both the two and type zero. Okay. P is a prime number, GL is the sequence power n group, and we denote, we take an integer n bigger than 1 and an integer q between 0 and we consider the heat, the heat action of the equilibrium, G and heat action of the equilibrium phase R L, and we know this space is ELN. Okay, so it's just a linear representation of the equilibrium. Orthogonal representation because they're formed by the people. Okay, AQLN stands for the set of PQ periodic points of ELN. It will be a linear subspace of the ELN. It's invariant under the action of ELN. Okay, and the complement is also invariant under the action of GM, and the complement we denote by ELNP. Okay, so actually we remove PQ periodic points for this. Okay. So ELN is a Euclidean space, EQLN is a linear subspace. We will take the orthogonal complement of EQLN. So it will be invariant under the action of GM because GM is by orthogonal transformation. Okay. We'll take the unit sphere in the orthogonal complement. That's it. The unit sphere will be once again invariant under the actions of GM. Okay, so we consider K and Q as the G space, the dynamical system. And once again,
So by each period points, you mean exactly this period or
most, not exactly. So it's most DJ power. Okay, okay. Okay. So this same period we denote by K and plus 1 use a set of PM periodic. So once again, with the orbits at most of the size e to the power. Okay. Now, something with properties of the spaces. First of all, K and U and E and U are GM homotopy. Okay, so let me remind you what G homotopy means. If we have two G spaces, okay, so G has an equivariant. Okay, now homotopy is defined on the product of the domain with a 0-1 interval. Okay, domain is a G space. If we consider the 0-1 interval also the G space with the trivial action of G. We consider the product action of G on the product of X with the 0-1 interval. Then we can consider homotopies it's meaningful to talk about G homotopies. Just G maps from the product of X with the 0-1 interval. Okay, and then we can expand on the notion of homotopy series, so to talk about G equivalence, G homotopy, and G homotopic map. Okay, so K, L, and Q, and P, L, and Q are GM homotopy. And this GM homotopy comes orbital star. So K and L lies in the orthogonal complement of P to the power of K periodic force. Okay, so we can take the projection of E and M to Z space. The projection will resolve the P to the power of K periodic force. Okay, and now we will take the regular projection from the origin from 0 to the unit sphere. The unit sphere is exactly K and Q. Okay, and it's easy to see that what we get is G homotopy equivalent. Okay, so in one way it will be just an invariant, and the other way comes from the radal top projection to K and Q. The second property is almost obvious. Okay, so we would just replace K by E. If I say everything here can be done with not this K and Q, but this E and Q. But K and Q is better because it's sphere, it's compact, and just Euclidean space without subspace. So we need to take care of some things related to spaces that are not compact. So we need to work on presenting the spaces with PW. So it's easier to work with the sphere. Okay. So we just so E and L is naturally embedded in E L prime because the Euclidean space is just bigger than we embed it in coordinate subspace. Okay, and from this embedding, so we can derive an embedding of K, L, and Q to the K, L prime, and Q. There is nothing big here. We can form verification of the property. And the second one is it's also obvious, but maybe slightly less obvious than the previous property. And it comes from because we changed here the group. Okay. So on KL plus one group, we have the action of the group of okay. Now we take the T to the power M periodic of that space. Okay, so if we take the subgroup H, E, T, okay, so this is the subgroup of G n plus 1, so index trivial on the.
Please don't find me.
Okay, so it acts trivially on this space. Okay, because P to the power n periodic points, so and the action of oh, I'm sorry, whatever. Oh, so index 3. Okay, now we need to connect. This one,
It was told that online participants cannot hear well. Now it should be
better.
better.
It's better not to hear what
Could someone confirm? Can you hear well now?
Hello, I can confirm, and it is better now.
Thank you.
Okay, okay, now we need to connect K and Q. So the connection comes from just the natural embedding of K M into E and okay, so this space is and to the far and this one is R and to the far and even here is the variance embedded and it goes this way. If you take here a point, okay, so this point will go to P up. Okay. So this map will be equivariant, okay, but because we are talking here about the unit field, we can turn it into isometries, into an isometry by not adding the constant here to preserve the norm of x. Okay, and this is exactly the map that will provide the isomorphism between Km and n plus 1 q and Km and q. And once again, consider Km the first space with the action of the quotient. Of the definition of the equivariant maps, it's equivariant, just the kernel of the equimorphism between Gn plus 1 and Gn with H. Okay. Here, actually, the superposition connect all the stuff with the positive from H. So, the position says that if X is a G and space that X does not exist a G and map to K and Q for Q between 0 and n, then every map from X to the Euclidean space Rn, there is a point such that the induced map FGN of the orbit of X was induced map FGN sends the orbit of X to a set containing the closed space e to the power k fold. Okay. And connected with the standard most Seward, just and the orbit of X the set containing the most p to the power k for this, so I will write an explanation of this proposition. So, okay, so we take from F from X to X on okay, and we can G then G. Okay. Space E U okay. So if for a point x in x, we have the f of g of x, and we have f to a point in okay. The whole orbit will be outside, the whole orbit will lie in this space, okay, with a consist of e to the power k periodic point. So the whole orbit will lie in this invariant subspace, and the orbit will be the image of the orbit will be all inside the key. Okay, so the only possibility when we will have the conclusion of this proposition does not hold is that we will not touch to this subspace of E and F. Okay, but when it happens, so we will have that this map will go to X to and complement of this. Okay, and this is the homotopy equivalent to K and M cube. Okay, so if this property doesn't hold, we will have a map to the complement. Okay, and because here we have a GM homotopy equivalence, okay, we will also have a map to this space. And this can be the assumption of this proposition. Okay, so we know that such a map does not exist. Okay. Okay. Now we are going to construct spaces which don't admit equivalent maps to G spaces K and M T. Okay. And the construction is already here in the previous slide to the domain now. So is the product of So for a sequence of natural numbers, then I, okay, we consider the product of the initial portion of the sequence from I equal to 1 to L of the sphere. And each sphere is considered with the action of the cyclic I group, and we consider this product with the action of with the diagonal action of GM. Once again, we just take the generators of each space, of each factor of the product, and the action of a generator of GM on the product will be just the actions of the generators on the coordinate space. This is just technical assumption.
It's confusing in the sense that when we take over the eye, so you mean on the coordinate we consider a demolar.
We take the action of the generator. So each sphere we have the action of TIs, homeomorphism. Okay? And then the action will be just the action of TIs on the coordinate. So here's the action of the generator. TI is the action of a generator of G.
That's not the sense that the diagonal action of GM. That's not the point.
But what is the diagonal action of G?
GM on each coordinate you have the whole GM.
Okay, but okay, you take T, and now the T will be P to the power n periodic, because you have here groups of lower order. Okay, doesn't matter. You can consider each space with the action of V. You want again to take a embeddable from Z to the cyclic group, okay? And you can consider each space here with GM action, just to take the epimorphism, okay, from GM to GI. Okay, okay, great. But we mean by the diagonal action that is the technical assumption that is obvious from if you take the standard action of cyclic groups on spheres. Okay. Recent issue on geometry. Okay, what it means, so the action is by simplicial, and in addition, we have a simplex invariant under the action of an element of the groups, and this simplex is the action of this element on that simplex is trivial. Okay. Okay. Not a restriction, because from any simplicial action we can go to, for any actions by simplicial maps, we can go to the post-polycentric subdivision and to get the property that if the simplex is invariant, then the action is trivial, not of the element.
So it's just correctly, if we take n I equal to 1, so we just have a circle and it's divided into segments with respect to e power m, right?
Maybe I think it belongs at the action. Maybe so, strange. Reaction. Okay, and there's the same definition of GCW complex, just instead of simplicial, actions by sequential maps, we take actions by cellular actions that send cells to cells and if the cell is invariant under the action of an element, then this action, the action of the element of that cell is triggered. Okay. So the main proposition is that for every prime p and every sequence of natural numbers L, Q, U non-negative, there is a sequence of natural numbers N, I, such that for each m bigger than 1, the Gm complex determined by P and the sequence Ni, okay, and using this terminology we refer to M as a Gm complex determined by P and the sequence. So each N does not admit a GM map to KLQF. Here you can see that actually we are proving a stronger function what we need for that Morgan of the Borsa-Kugel theorem. So if we take in sequence then U plus 1, okay, we will get that's the map to RQ to RK. The map induced by a map to RK will send a certain orbit to space with most p to the power k minus 1 point. Here, actually, we the dimension of the Euclidean space we improve to r to the power n. Okay. So, to the power q. Okay. So if we take the dimension by 1 because the dimension so for every okay to u okay we will have okay that it will stand in orbit. Okay, I don't mention that. I believe I didn't have this slide. Anyway, in order to get the time that the Borsa-Kugel theorem that we need, or we stated earlier, we need to take the sequence LQ equal to Q plus 1. Okay? Q plus 1. So it's a more general result. Okay. Now, first of all, I would okay, I'm sorry. So what I wrote before was meaning, completely meaning. It should be this one. Okay, Borsa-Kugel type theorem. So if we have a sequence of any sequence of natural numbers, and by our previous proposition, we can take once again, we are taking this sequence. Okay, this is the part of the structure. Spaces that each and n does not admit the GMF to K, L, Q, and Q. Okay. So we take the sequence Ni produced by the main proposition. Okay? And now we consider the inverse limit, or it's the same, consider X to be the product of all the spaces, all the sphere. Okay. In order to be consistent here, once again, we can consider each and M with the action of C. Okay. And M is a bonding net in this sequence. Okay, so each and M is the drawing. And here. And from each here, the action G. Okay, so here. Okay, and we have the action and on the product. Okay, so I call the product action. Okay, so if we can plus one, we have okay. So we can take the projection. The projection will be the equivalent. Okay. And once again, we return all the groups of G I's to the action to 3. Okay. We don't have in the system of G spaces with bonding maps being equivalent. Okay. And it will determine the inverse, so the inverse limit is well-defined. Okay. And we'll have the ZH of the inverse limit. Okay. Another way to interpret that, if we consider the generator of Z and the action of P on X, and we will take the I coordinate, so it will be the action of the generator. Okay, and here you will be in the which is the product, the product. I goes for 150. Okay, so we define the action of the generator of V by this formula. Okay. Okay, so on each product, the action will be periodic, but if we consider the action on the product space, okay, the action will be free because the order of the groups, so on each factor, the action is free, but the order of the group goes to infinity. Okay, so we will capture in a sort of coordinate. Okay, the action will distinguish only 2 points of any order. Okay, so we will define a free action and just relatively trivial consequence of the main proposition, okay, which is exactly equivalent to next one, that M does not admit a GM map to K LMQ. Okay, the property together with the previous propositions that we can interpret this in the way of the side of the images of the orbit, we can get the conclusion of the proposition for every map from X to R to the power LQ, there is a point in X such that at V send the orbit of X to a set of sides at most P to the power K. In particular, we get that F send the orbit of X to a set of sides at most P to the power K. But we don't need that property just to connect it with usual volumes of the Borsuk theorem. Okay, the proof is simple. Okay, it's nothing deep so far. Okay, you can get this Borsuk this conclusion from the previous proposition. Yes, you can get it if you exercise. Because yes, okay. I can try to prove it, but most likely I will make a mistake and the talk will last forever. But it won't happen. Now, the problem is what I want to say that the heart of the business is here in the main proposition. Okay? And there are a lot of versions of both the Coulomb theorem and a lot of techniques are used to prove more advanced, even very advanced, like K theory, the covariance, and actually every year here's something new, but still, okay, I don't say that we try to use all known methods, but at least we try to use case theory to prove this theorem, and it came from it was originated in the work of Markov. Okay, if you take the standard Borsuk-Coulomb theorem just for one sphere and the map to R, okay, or to Euclidean space, and you want to know if you will find an orbit going to say single in the image, okay? Okay. It's already non-trivial if you take the action of cyclic group, not completely trivial if you replace the Z2, okay, just just to reflection with respect to the origin by the p-cyclic group, just the p-cyclic group, okay? It was proved in probably even the 60s, I believe, at least it was also proved by Markov, but if you replace a cyclic group, a p-cyclic group with prime order by a cyclic p to the power k, by cyclic p group, okay, it becomes much more complicated. Even for one sphere, it was proved maybe around 80s by Markov, and he proved to use a complex case theory. But there are some generalization, but still, so we couldn't apply known techniques to prove this theory. And we worked hard. So it's more than half a year, we probably From the beginning, the approaches were stupid, but at last, maybe it was not precise, but somehow there was a reasonable argument that case theory does not provide an abstraction to existent methods that we want not to even. So the breakthrough came and we realized that we can apply the total projection and the other completions of the complex that we want to bring. Okay. Okay, so okay. So the way we prove that result by just a minor modification. We replace the space with the space K N U M U by its theory completion. Okay, by its theory. So here, okay, I will state a few properties, but before I will say a few words about the theory completion, I just point out that from that stronger version, that version is indeed stronger than the main proposition. Okay? Because if we take the theory completion of K, then K it needs GMF, GMF to its theory completion. So if we go back to the, if we are able to construct a sequence of NIs having these properties that each NM does not admit a GMF to the theory completion, okay, and K admits a GMF to the theory completion, we get that also K and QM Q there is no GMF to the space without the theory. Because otherwise, if there is a map without the theory completion, we combine that map with the GMap to the theory completion and get a contradiction to this result. Okay, so this result indeed implies the main proposition. Implies by this property that K admits the GMap. Okay. Here I try to cite the result. So most likely some of all of them know, but we couldn't find references. But it's more or less that what we need from the theory of theory completion. There are two approaches, maybe more than two approaches for theory completion. Okay. Theory completion it's a slightly strange tool in algebraic topology, but it's more or less it's a function. Usually in algebraic topology, you consider functions to some objects having algebraic structure, like homology, cohomology groups. Here, it's a function for topological spaces, Q-topology. Okay, but nice spaces, having some additional properties that help to start the general topological space. Yeah. In order to simplify the setting, we will talk about simply connected spaces. For simply connected spaces, we have no complications in constructing p-adic completion. As mentioned, there are two approaches: the topological approach, that is, I mean, the constructing p-adic completions by vibration, and combinatorial. Both originated in the work of Kahn and nicely presented in the book of Buswell and Kahn. So the localizations, completions, I don't remember the type. Okay. So following that book, okay, we can consider the p-adic completion as a function from a category of G spaces and G maps to itself. Okay. So if you have a GCW complex, then its p-adic completion is again a G CW complex. Now, it's a function. Okay. Then if we have a G map between two G CW complexes, it will induce G map between the p-adic complexes. But also in this way, we can turn into every GCW complexes again into a GCW complex. So in Buswell and Kahn, they are not talking about the equivalent versions of the construction, okay? But the construction is factorial. Okay, so if we have an action of element of the space on CW complex, it will induce the corresponding action on its p-adic completion. And that way we can turn, consider the p-adic completion as the G space again. Okay, so we can consider the p-adic completion on the category of G complexes as a function of the category of G complexes to itself. Okay, so the first property I mentioned actually leads to proving to deriving from the p-adic version of the main proposition, the initial version. Another property, by the way, so we don't need all the assumptions that I wrote here. We have general assumptions for all the statements. Okay. For some of the statements, we don't need so strong, the examples to be so strong here, but okay. But this is what we do. Now, by a CW complex, GCW complex or G space, we denote by so we have a G space, okay, and H is the subgroup of G, normal subgroup. Okay, actually not only normal, we can consider any subgroup. So this is the fixed point set of the action of H on K. Okay, so this is on the point in K. I'm saying X is equal to X, so maybe K in K. And K is subgroup of okay. So this is the well-known property of the p-adic completions that we can take the fixed point set of the action of H and to take the p-adic completion, and we can take first the p-adic completion and after that to take the H fixed points of the action. Okay? The spaces are not the same, okay, but it can be shown that they are G homotopy. Okay? Another property is that if we have a finite GCW complex, then its periodic completion, then there is a tower of vibration that I denoted by omega I, omega I, omega is it's capital omega I and small omega I is a bonding net. One can construct the tower of vibration, so it's inverse linear, such that each element of the tower is a GCW complex, having finite homotopy groups. And the bonding maps are vibration, okay, tower vibration, but in addition to being vibrations, they are also G maps. Okay, then we can construct the inverse thing. Okay, the inverse thing will be again a G space. We can denote the space by omega. Okay, then the periodic completion of K will agree a G map to the inverse limit, which is also a weak homotopic. Okay, so it's quite a standard problem if we don't consider equivariant maps just periodic completion of the topological space. The problem is it is also known for in the equivariant setting, but this result is not very complicated. It's derived once again from what is presently in the book of Buswit and Kahn. Okay, okay, so all the theory of periodic completion is not completely trivial, or it's completely non-trivial. Okay, it's the whole theory. But inside the theory is really tough result. Okay, the so-called equivariant Sullivan conjecture, the generalized Sullivan conjecture, and it says that if we consider the space of all the equilibrium, so I'm talking about this map PG. Map means maps from one space to another. G maps, equivariant. Okay. We consider only equivariant maps from EG to the periodic completion of P with a compact open topology. Okay, this is EG. It's a contractible GCW complex with a pre-action of G. Also, universal cover of the island of MacLean complex. Okay. So we consider this map, and we identify the constant maps in this space with the fixed point of the action of G on K. Okay. Okay, the constant map is essentially formed to a singleton. So that singleton must be the fixed point of the action of G on the target. And then the inclusion of this subspace of the mapping space to the set of the space of all the maps is a big homotopy. Okay. The Sullivan conjecture was posed by Miller after he moved his the initial version of the Sullivan conjecture for trivial actions of G on spaces. And the generalized parallel conjecture was proved independently by Carlson, Lenz, and Weyer, Miller, someone else. Okay, it was proved in 90s, this century. Okay, this is more or less what we need for proving that the periodic strengthening of the main proposition. I have a few more slides. With the outline of the proof. I can show you. So we will go. Okay. There is no. I believe I do not have time to go through those slides. I can open the video will show but just using the correct, it can be shown that everything. So we don't need nothing else in order to get that proposition. So all the data or all the results from periodic completion are here based on the results, ordinary techniques for topology, working with vibration, with the thermal conjecture, we can prove magnetic result. So I believe it's right moment right for microscope.
So are there any questions? Yes, wherever it appears, I don't think it's so useful.
So we will start to count only iteration of the inductive program. They are passing from M plus from M to M plus one. Okay. That means that we can increase the dimension of the sphere, okay, and we can always get a map to the periodic completion. Okay, we can do it for infinitely many spheres. Okay. And the beauty of the periodic completion is that if you take the model of the contractible space EG with the free action of G, that we can construct a map to replace it here by the contracted space. Okay, the physics property of periodic completion. So a priori we know that we can, the main proposition is okay. Maybe there is another way to prove it, not using periodic completions, but it looks like not being easy task. Okay, so it's a specific property of the periodic completion. Now we replace here by constructed. And we have the Tolman conjecture. Okay, in that interpretation that we can use it like the Begley-Vittori's theory. Okay, so from this we can factor the map through NM. Okay, and to get a contradiction with our assumption. So we assume that for NM is everything is okay. Okay. We need to slightly adjust because for NM we are talking about the space with K and QMT. So we need to pass from m plus 1 to m, okay, but technical, the technical issue. Okay, so the non-constructive way is here. So we are assuming that does not exist for any, but we get a contradiction. Okay, so this part is not constructive. It's just about existence.
Are there any other questions? Yes.
So you mentioned at some point that you can get the Borsuk theorem for more general spaces than RK. Can you comment?
But,
So we have a statement that
both
about
equal
embedding
theories.
into RF, right? Maps.
Ah, not both equal about embedding result.
Right.
Yes. Actually, it can be extended that result that there are reactions not embeddable into cubical sheet for any infinite subgroup of countable product of finite p groups. P groups. P groups. So it covers, for example, the actions of Z. So Z is a subgroup of the product of cyclic groups.
But I think the question is about the cubical sheet by M. The right hand sheet. What do we get there?
Okay. Okay. So to replace it by what? By finite dimensional space or?
Let's say change the alphabet in the cubical sheet,
Okay. Subshift, you mean?
for instance.
Okay. But if you cannot embed it in the whole, the full sheet, then you cannot embed it in a subsheet.
No, but sheet over a different alphabet.
But on what? On the finite dimensional space?
Yeah.
But it will be a subshift of R.
Yeah.
So you probably mean that a sheet on an infinite dimensional space, okay? But on infinite dimension, you can embed, yeah.
The other question, I think I saw somebody want to ask. Okay, if not, let's thank you.